Today we are going to learn about spontaneous emission and how it applies to lasers. Lasers are amazing light beams, powerful enough to zoom miles into the sky or cut through lumps of metal. Although they seem pretty recent inventions, they've actually been with us over half a century. The theory was figured out in 1958. The first practical laser was built in 1960. At that time, lasers were thrilling examples of cutting-edge science. Secret Agent 007 James Bond was almost chopped in half by a laser beam in the 1964 film Goldfinger. But apart from Bond villains, no one else had any idea what to do with lasers. Famously, they were described as a solution looking for a problem. Today, we all have lasers in our homes, in CD and DVD players, in our offices, laser printers, and in the stores where we shop, barcode scanners. Our clothes are cut with lasers. We fix our eyesight with them. And we send and receive emails over the internet with signals that lasers fire down fiber optic cables. Whether we realize it or not, all of us use lasers all day long. But how many of us really understand what they are or how they work? In this video, we'll learn about what spontaneous emission is and also how we use it to make lasers work. Before we begin our talk about spontaneous emission, we need to review what we know about the atom. Just like bricks are the building blocks of a home, atoms are the building blocks of matter. Remember, matter is anything that has mass and takes up space. All matter is made up of atoms. The atom has a nucleus, which contains particles of positive charge, the protons, and particles of neutral charge, the neutrons. Surrounding the nucleus of an atom are shells of electrons, small negatively charged particles. These shells are actually different energy levels, and within the energy levels, the electrons orbit the nucleus of the atom. So talking about the electrons, there's a place called the ground state. The ground state of an electron is where the energy level it normally occupies. It is the state of the lowest energy of that electron. When an electron temporarily occupies an energy state greater than the ground state, it is what we call an excited state. An electron can become excited if it is given extra energy, such as that from a photon, which is a packet of light, or it collides with a nearby atom or particle, with something to supply it with energy. Each orbital has a specific energy associated with it. For an electron to be boosted to an orbital with a higher energy, it must overcome the difference in energy between the orbital it is in and the orbital to which it is going. This means that it must absorb a photon that contains precisely that amount of energy, or take exactly that amount of energy from another particle in a collision. Electrons do not stay in excited states for very long. They soon return to their ground states, emitting a photon with the same energy as the one that was absorbed. This emission of photons is light, and this is what spontaneous emission is. Let's delve into spontaneous emission in a little more detail. Taking the electron transitioning associated with visible and ultraviolet interactions with matter as an example, absorption of a photon will occur only when the quantum energy of the photon precisely matches the energy gap between the initial and final states. So that's here. And Planck's equation tells us what that energy is. In the interaction of radiation with matter, if there is no pair of energy states such that the photon energy can elevate the system from the lower to the upper state, then the matter will be transparent to that radiation. It'll go right through. Energy levels associated with molecules, atoms, and nuclei are in general discrete quantized energy levels, and transition between these levels typically involve the absorption or emission of photons. The electron energy levels have been used as the examples here, but quantized energy levels for molecular vibration and rotation also exist. And we can see that the energy that it takes for it to come up is also the same amount of energy that's released when it goes from the excited state back down to the ground state. And this is, when we talk about spontaneous emission, that is the electron going from the excited state back down to the ground state and emitting this photon of energy, or this light. Now, the rate of this spontaneous emission was identified by Einstein as A times C. And this is where C is the concentration of absorbers in the upper energy state, and A is the Einstein coefficient of spontaneous emission, and is given by this equation here. Now, a couple things. You got A, you got pi, you got E, which is the charge of an electron, 1.6 times 10 to the negative 19 coulombs. You got the permittivity of free space, you got the speed of light, and you got the mass of an electron. And you just take those two, and that shows us how much emission will occur, how fast it will occur. Now, what we know now that we know about spontaneous emission, how is it used in lasers? What do you need to make a laser? You need two basic parts. You need a load of atoms, and it can be in any state of matter, with electrons in them that we can stimulate. This is known as the medium, or sometimes the amplifying or gain medium, because gain is another word for amplification. Two, you need something to stimulate the atoms with, such as flash tube, like a xenon flash lamp in a camera, or another laser. A typical red laser would contain a long crystal made of ruby. The medium, we're going to show as a red bar, with a flash tube wrapped around it. The flash tube looks a bit like a fluorescent strip light, only it's coiled around the ruby crystal, and it flashes every so often like a camera's flash lamp. So this would be here. Now, how do the flash tube and the crystal make a laser beam? And we'll try to explain this diagram. So we go down to 1. This is a high voltage electric supply. It makes the tube flash on and off. So starts the flashing of the tube. Then we go to step 2. Every time the tube flashes, it pumps energy into the ruby crystal. The flashes it makes inject energy into the crystal in the form of photons. 3. Atoms in the ruby crystal, the large green blobs, soak up this energy in a process called absorption. Atoms absorb energy when their electrons jump to a higher energy level. After a few milliseconds, the electrons return to their original energy level, the ground state, by giving off a photon of light. And that's the small blue blobs you see. This is where spontaneous emission is occurring. 4. The photons that atoms give off zoom up and down inside the ruby crystal, traveling at the speed of light. 5. Every so often, one of these photons stimulates an already excited atom. When this happens, the excited atom gives off a photon, and we get our original photon back as well. This is called stimulated emission. Now, one photon of light has produced 2, so the light has been amplified. In other words, light amplification, an increase in the amount of light, has been caused by stimulated emission of radiation, hence the name laser, because that's exactly how a laser works. 6. A mirror at one end of the laser tube keeps the photons bouncing back and forth inside the crystal. 7. A partial mirror at the other end of the tube bounces some photons back into the crystal, but lets some escape. And then lastly, 8. The escaping photons form a very concentrated beam of powerful laser light. So that's how a laser works. It starts with spontaneous emission, and then spontaneous emission, the photons produced in spontaneous emission then strike another excited atom, which then causes stimulated emission. And the stimulated emission produces extra photons. And all this extra photons then can be focused through a point, and that's where a laser occurs. So hopefully you have enjoyed learning about spontaneous emission and how it makes lasers work. If you have any questions, please do not hesitate to contact me at my email, which you can see there, jjohnson1@plymouth.k12.in.us, and I will try to help you out, or at least give you a place to start looking for your answer. Thank you for watching.